In this video, we're going to introduce some simple properties of measurable functions. Let's start with the following proposition. Suppose I have a continuous function on some metric space. Then let's equip the metric space with the usual Borel sigma algebra. Then this function f is also measurable. Okay, so basically continuous functions are measurable. The proof is really simple. So the continuity, there's an equivalent definition. It's basically saying the inverse image of every open set is also open. So this is for every U open set. So we know the open sets in R generate a Borel sigma algebra, and the inverse, because it's open, is inside the Borel sigma algebra on X as well. So this follows from the previous lemma from our previous video. So f is this f inverse of u is inside B of x. So we know f is measurable. Okay. Well, I shouldn't say the other direction. It should imply the f is measurable. Okay. All right. So that's quite simple. And as a quick corollary, so suppose I have some measurable functions and I want to compose them. So let's say I have a f that maps x to y, and then I have a function g that maps y to z, and let's suppose x has a sigma algebra A, y is equipped with the sigma algebra B, which is the same, and z is equipped with the sigma algebra C. Okay. So I want to show that their composition is also measurable. Okay, so then if I do the composition, so how do I do that? I need to have a G first, G composed with F. Okay, so that's essentially takes an X from X, that maps it to F of X, which is in Y, and now we apply to G. Okay, so this is a function starting from X through Y and end up in Z. Okay. So I want to show that this function is measurable. Okay. The proof is also really just basically one line. Okay, so you take any E that's inside the sigma algebra C and you consider its pre-image under this composition. So you consider this pre-image of E, and you can just first pull back using the G inverse. It's basically G inverse of E, and then you pull back using the F inverse. Okay. G being measurable tells you G inverse E is inside the sigma algebra on Y, which is B. And because F is measurable respect to the same B, so this F inverse is in A, so the whole thing is in A. Okay, so we get it's measurable. And basically, a quick corollary how we're using it is the following. So usually what happens is if you have a function G, which is, let's say, from R to R, a continuous function, well, then we know it's measurable with respect to the Borel sigma algebra on R. And suppose I have some function f which takes a value from x to R, which is also measurable. Okay, then because continuous function g is measurable and f is measurable, then what we know is that their composition is also measurable. So g composed with f, which now is a function from x to R, that's going to be measurable. Okay. So for example, if you take g of x equals to x squared, then this basically tells you if you have a function that's measurable, then f squared of x, okay, that's also measurable. Okay, of course here f is itself measurable. All right, so those are very simple properties. Let's move on to some slightly more tricky ones. So here's the proposition. I want to show measurable functions. They are both linear and you can multiply and you can take their inverse. Okay, so here's the proposition. So let's say f and g, they're both from x to r, they're measurable functions. Then I want to show the following. So suppose I have some lambda, a scalar inside R, and you can do the linear combination f plus lambda of g, which again is from x to r. I want to show that this one is measurable. And you can also multiply them. You can show the f times g. Okay, so basically you multiply f with g. Okay, so this is also measurable. And finally, I want to divide them, but to divide it, I really require that g need to be non-empty. The f of x divided by g of x. Okay, this is also measurable. Okay, so basically measurable functions are preserved under these linear combination and multiplication and quotient. Okay, so they're really forming an algebra. Okay, so the proof, let's prove the first one. Okay, so let's to show the first one, we really need to show is basically I can multiply a scalar and I can add two things up. So let's do the scalar first. Okay, so let's fix lambda. Let's say lambda is greater than 0. And you can consider lambda g, and if I want to show it's measurable, I just need to show its pre-image of some collection, say negative infinity to a. That's going to be a measurable set. Okay, so this is follows from the lemma from last video. So this set is essentially all the x where g of x is our lambda g, this function evaluated at x is less than a. And because lambda is positive, this is all the x where g of x is less than a divided by lambda, which you can write it as g inverse of this negative infinity to a over lambda. Okay, and you know g is measurable, so this is measurable. So this basically, let's say, is inside B. Okay, so here x is equivalent to the sigma algebra, let's say B. Then this essentially shows that lambda times g is measurable. Okay, so that's quite simple. Now let's show that we can add two things up. Okay, so let's consider f plus g. Okay, this is slightly tricky, so let's consider f plus g inverse of a negative infinity to a again. Okay, so again, this is essentially all the x where the f of x plus g of x, their sum has to be less than this fixed number a. Okay. Well, if you think about how can a sum be less than a, well, you can divide them up. Okay, so you can say, well, where is f? Well, f may be less than some number, let's say r here. Okay. Then if f is less than r, then g has to be less than a minus r. Okay. So here R can be really anything, okay? I want it to be a countable union or intersection. So to make it countable, I can just let R equals R inside Q, okay? So you can convince yourself these two are really the same. Depending on how large your fx is, you can pick some R, some rational number that's close enough to f of x, and you can make some room to make g of x less than a minus r, okay? And if you write it this way, then this is essentially, you can break the set as all the x where f of x is less than r, and you at the same time you require all the g is also less than a minus r. So here r is fixed. Okay, so I'm taking the intersection of these two things. And because f and g are both measurable, these two are basically the inverse image of their negative infinity to r or a minus r. So we know this is inside B. This is also inside B, and their intersection and countable union. So whole thing is inside B. So this basically proves that f plus g is also measurable. Okay. So now I have f and g, their linear combination is measurable. Why? What about their multiplication? Well, there's a really simple trick. Okay, so if you follow Ken's note, he's following a more traditional version. I'm using a slightly simple trick. So if you consider f times g is really just a linear combination of these things, so you can take f plus g squared and you minus the f squared, you minus the g squared. Well, that will give you 2 times fg, so you need a half, okay? So we saw that f plus g is measurable, and you compose with a continuous function which takes the square. It's measurable, and similarly f squared and g squared, they're all measurable. So you take their linear combination, which give you f times g, so f times g is measurable as well. Okay, so this is slightly simpler than Ken did in his note. And lastly, I want to show that when g is non-zero, then the f over g is measurable. Well, the f over g is really the multiplication of f times the constant 1 over g of x. Okay, so it suffices to show that 1 over g of x is measurable. Okay, so let's show that. Here's the claim. 1 over g of x is measurable. So to show that again, you just need to consider its pre-image of something. Let's say x where 1 over g of x is less than something, let's say a. And there are really 3 possibilities this set, depending on whether a is positive, negative, or is equal to 0. So let's say there are 3 things. So when a is negative, when a is equal to 0, and when a is positive. Okay, so when a is positive is probably the easiest. You just move everything around. So when a is positive, then the g of x can be either negative, or if it's positive, then you can move it to the right hand side. So it's all the x where g of x is greater than 1 over a, or when g of x is negative, less than 0, then of course 1 over g is negative is less than a, which is positive. So it's the union of these 2 things, and they're both measurable. Okay, so this is inside B. When a is equal to 0, that's also very simple. This is simply 1 over g less than 0, which is basically when g is less than 0, so you know this is measurable. And the more tricky one is when a is less than 0, then 1 over g is less than a, which is less than 0. So first of all, you know g has to be less than 0. And because it's less than 0, you multiply g on the right, and then you multiply a less than 0 a on the left, or 1 over a on the left, then the inequality changes sign twice, so it didn't really change, so you end up with something like that. So this is just the g inverse of the open interval from 1 over a to 0, and it's again inside B. Okay, so in any case, we know that this is inside B. Okay, so this essentially just proves that 1 over g is a measurable set or measurable function, and we can multiply with f, so f over g is also measurable. Okay, so this finishes our proof.